one knows why. And sorry for my English, that is probably even worse. If you don't understand something, please raise your hand, try ask, repeat, whatever. Okay. Today is about ZeroMQ. Okay. Let me say that it's difficult to explain what ZeroMQ is, because it's a low-level framework. It's pretty technical, and it's not easy to describe what it is. I put a slide to describe what it is, and it is the last slide. I'd like to show you what ZeroMQ can do and which kind of functionalities we can implement with ZeroMQ. Maybe it's better to understand what it is. I'd like to start saying why I'm using ZeroMQ and why I'd like to show you ZeroMQ and to present this framework. Some background. I'm working basically in two different environments at the moment. I'm working in the cloud computing business, because it's impossible to work in cloud computing if you are in IT. And I'm working in the embedded environments. So I'm designing operating systems that are working in a kind of small, or not so small sometimes, devices, and applications that are running in the cloud that are able to integrate with other elements, components, agents. And in the last year, ZeroMQ really made my life much easier, very easier. Because at the moment, the big problem with these technologies is to make possible to have a communication layer that is very easy to manage, that is very efficient, it's very reliable, and you can learn in just a few hours, because usually you don't have the time to implement everything from scratch, from sockets, threading, and blah, blah, blah. So the first thing is ZeroMQ is something easy, first of all, and make possible to write easy application. Let's start with the classical big problem that everyone has, scalability versus complexity. This is a chart that probably you know. You have complexity, okay, and you have you have your application with one thread, maybe two threads, maybe more threads, some multi-threading applications. Maybe you want to scale your application on multiple nodes, so you want to create a distributed environment where applications are able to distribute their workload, for example, so you have nodes and not just threads or processes. And you want to be, you want to write something easy when you write a single thread, single process, single node application, and you want more or less the same complexity when you are in a very complex environment. It is what you want. But you know the reality. Reality is not that. This is what you have usually. Write an application where you have just the main, okay, print, well, it's not difficult. Easy to debug, easy to test. And you introduce the second thread. Okay, it's a big mess. Race conditions, semaphores, you have problems of synchronizations, and I'm not speaking yet about Python, okay? I'm just speaking about taking two processes and try to have an inter-processes communication. It's a mess, usually. And when you want to scale in a big infrastructure and you want to put nodes that are able to cooperate for a specific reason, complexity is increasing and increasing and increasing. So this is what you have usually, and unfortunately, it's very hard today to be in this situation. If you're writing an application that is using one thread, one core, one machine, it sounds too easy to do here today. That's the problem. So we are here, and we want something easy. That's the point. And that is what ZeroMQ can help you do. ZeroMQ has MQ in the name. So let's see what the Q is, or at least what the MQ is. Q is about Q. So this is a Q. Okay, we know these very detailed, so we read. And when we have a car, a Q is not something too difficult to be managed. You are in your car. You don't have to go too fast because you crash. You don't have to go too slow. You have to stay in your line. Okay, it's something that we really are able to manage without any problems if we are not around people like me a few hours ago. So this is something that usually works pretty well. It's a model, it's a real model in the real world. That is easy, it works, everyone knows this model. Well, the Q in the T actually is this one. When we want to implement the same model with software, this is the result. Always, okay, always. It's very easy when you design your software. You say, okay, I have to put one thread, I have one data, I can access this data only with a locking system. Very easy, implement this, that. You run the software, and this is the result. Always, okay? If you don't have these results, okay, be careful, because in production, one day you're going to have that result. Always. So, queues are easy when you are thinking about queues, but they are a mess when you try to implement them in the proper way, especially if you want to run maybe with queues and sending messages between different elements in your networks in a very reliable way, okay? Because it's something mission critical if you are on the car in this case. So queues usually are implemented in mission critical environments. This is the same thing with C++, so okay. Now, let's see the zero in the ZeroMQ. Okay, it's not really a zero, but let's see ZeroMQ. There is a long story about the symbol. You can go to the internet and found all the history about that. Anyway, why the zero? So if the M and Q are for messages and queues, zero is, first of all, because ZeroMQ is something that is zero broker. So there is no broker in the architecture of ZeroMQ. If you know how the classical enterprises queues systems or ESB or whatever you want to call them, they are usually based on an application called broker that is able to manage the queue, manage the messages, are able to do the persistence, and some other fancy stuff. They are usually very expensive, they are usually your bottleneck, they are usually a lock-in to keep customers on a particular product, and they are not very scarce. They can't guarantee you a very huge scalability most of the time. So the first goal of ZeroMQ was zero broker. Then, year after year, month after month, it was something more, zero latency. It's not really possible yet, at least quantum computing can help, but at the moment the idea is that we should try to have the lowest latency possible implementing ZeroMQ. So if I want to send a message on the network from one node to another node, I don't want to wait 10 minutes because ZeroMQ wants to optimize the communication. ZeroMQ just trying to reduce the latency. And reducing the latency is not just about sending the message as soon as possible. It's also reduce the size of the message. If I want to send a message with ping, and I have to create a protocol in XML with 200 lines of XML to describe how this packet is made, okay? And maybe I have 5 handshakes before the 2 endpoints can read and send and check and be sure that the message is passed through. Well, it is not zero latency, you have a huge latency. So ZeroMQ is to reduce the latency. And then, of course, the idea is to remove completely the administration step. Why? Well, you don't have the broker, so you don't have to install any service to run a ZeroMQ application. It's a framework to write your applications. It's not an application that is part of your infrastructure. That is the big part. And then, of course, we have cost, we have waste, you know the whole marketing stuff about that. So, the zero is about something simple, something brokerless, completely brokerless, and as fast as possible. And the ZeroMQ is really about sockets. Why sockets? Well, sockets are mandatory today. If you write an application that is not using a socket, you're doing something wrong. Because today application needs to use a socket. Not just the I and Emacs. Well, Emacs uses everything, but the I doesn't use sockets, for example. Okay, it's the only application probably. Applications today are web-based, they are cloud-based, They are fancy, they have a lot of features, and they always are using different elements in the network to send and receive information. Always. Okay? So sockets are mandatory. The problem is that they are complex, very. So ZeroMQ implements different kind of sockets, and it completely hides the complexity of a socket end-to-end communications for the developer. So we have to use sockets with ZeroMQ, but not the sockets that we know so far. They are completely new rendered sockets. They can be unicast, TCP, for example, but they can be also embedded or in memory sockets, IPC. Okay? So you can use a fake socket just to make possible for two applications or two threads to communicate with each other. The IPC or the improc sockets type in ZeroMQ are not sockets exposed to the network. They are just available on the same machine. They are for intercommunication between processes. But in all these cases, the API to access the sockets is always the same. So there is no difference, zero difference at all between a socket open on a same machine to make possible communication between two threads and a socket open on two machines to make possible to communicate in the network. There is no difference at all. Okay? It's just part of the configuration of the framework. It's not about how you have to write your application. We have, of course, some multicast transports. Multicast is something exotic, usually. So it is possible. My experience is not sometimes so useful. Very useful in few environments, and they are very strange. These are the closely supported. Anyway, it works, and again, they are completely abstracted for the user. So the multicast is made under the hood. Connect and bind are independent. What does it mean? Well, when we think about sockets, we always should think about a server and a client. Someone opens a socket, someone is able to connect to that socket and send data across. If a client tries to open a socket to a server that is not running yet, you have an error, right? And the server is not able to reach a client because it's the client that has to start the communication. This is the basic rule of sockets. Well, not in ZeroMQ. In ZeroMQ, a socket is just an abstraction of real socket. So you have to start a client, you have to start a server, means bind and connect. But the order doesn't matter. You can start a client, the day after you can start a server, and client servers are able to go to each other. That's it. You don't have any exceptions, you don't have any problems, that's completely fine. A server can send a message to the client. No problem, okay? You don't have to open a backward sockets, or you don't have to open a redirection, nothing. It's just a pure direct connection. Very, very easy, okay? They are always asynchronous. What does it mean? Well, let's say you have an application with only the main, only one process, only one thread, one machine. You open a socket, you write something in a socket. Your application usually is waiting on the socket. So if you have to send a packet that is 1 gigabyte on the network, well, congratulations, you designed a very well protocol, probably, but the point is your application has to wait 1 gigabyte of transfer before proceed to something else. Or you have to write something to use another thread to make the connection a big run connection. But if you start to put another thread in your application, you have complexity and you have to manage the various conditions and blah, 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 blah. So you start to use complexity. With ZeroMQ, everything is asynchronous. So if you say ZeroMQ, send something on the network, well, 1 millisecond, maybe less than 1 millisecond, but after that call, you don't have to wait to write something on the queue and to wait ZeroMQ to take something from the queue and send on the network. It's always asynchronous, and you don't have to write any extra thread to manage that. That's very important. That's very important also to understand that everything you write on a socket is always in the ground. And to help you to write good applications, okay, there are patterns that we can use. So we can configure our application to use a specific pattern. And using a specific pattern, we are sure that we are doing a good, hopefully, design of the application. The problem of multi-threading is that developers introduce usually multi-threads and multiprocessing to fix problems, not by design. You discover that if you have to write 1 gigabyte on the network, you have to wait a lot and the application is not responsible during the transfer, so you introduce a thread for that write. But it's not part of the design, it's part of the fix. And that's why we have a mess usually managing the queue. Queues are not easy to be managed. How long is the queue? What do you do if the queue is full? How do you clean the queue? How can you make persistent the queue? All these questions are a problem for developers. ZeroMQ, it is managed by the pattern. You have to choose a pattern, and the pattern says the queue is made in this way, the calls are made in this order, and you know everything about that. And last but not least, sockets are not one-to-one. I can open a socket to 5 servers, and I can read a response for all these servers in once. So it's not necessarily, even with the unicast transport, it's not necessarily one-to-one. Okay? These are sockets in ZeroMQ. And of course, it's an open source project with support, business support. It's available for a few languages, everyone, basically, even basic, that you see, Lada, C#, Go, Ireland, whatever. It's extremely easy to write because it's part of the design. It's very easy to write new bindings. Okay, but if you the use languages, so that's what we have, and it's cross-platform. Now, you should ask me, cross-platform. Well, we are in a Python conference, so is this written in Python? Well, the response is no, it is not written in Python. ZeroMQ is written in C++, and we have a binding for Python. But the core is still at different courses with different architecture, and it's not a service, it's just a framework. But it's written in C++. Now, if you have a laptop, and you have a laptop, you can go to this, the second one. This website is a very, very nice guide about ZeroMQ. And I took a few examples from that guide. So we are going to see some patterns now, to run some patterns and see what happens doing funny stuff. You can just follow the same examples, just downloading example, source code, everything from that website. Okay? It's Creative Commons, so, and it's very, very well made. If you click here, you can see also that this guide, the guide is multi-language. So for each example, you can have the version in C, C++, C#, Java, Perl, Python, blah, 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 blah. Okay? So it's very nice actually to compare how difficult and how easy it is to write the same code in different languages. And if you have a client writing in Perl and a client writing in Python, it's not a problem. ZeroMQ is completely hiding the complexity of exchanging information between different languages, even different architectures, even different legal and the other words. Everything is completely abstract. So let's start. Few basic patterns. These are the 3 main patterns that you can use to write your ZeroMQ applications. Request reply, publisher subscriber, pipeline. These are also the logical patterns. There are a lot of other patterns, but the other patterns usually are made to scale your application, or to increase the security, or to increase the distribution of your application. These are the logical patterns. So when you think about an application, usually you think about one of these. Okay? Very quickly. request reply, HTTP. You have a client that is sending a request and is waiting for a response. That's it. The communication is done. It's really like HTTP, okay? It's really like HTTP. But it's not HTTP. Publisher and subscriber. You have something that is sending information on the broadcast, let me say, to everyone, and subscribers that are listening to these messages. They can be there, maybe they are not there, they can lose messages, they can wait forever, they can be flooded by the messages. Just someone is writing, someone is listening. There is no request from the subscriber to the publisher. It's one-way communication, almost. And then pipeline. So you have a message that has to pass through different steps, one by one, to reach a destination. So you have a kind of workflow here. Let's start with the first one. Request reply, the easiest. We have a code here, okay? This is a hello world, basically. It's in Python, of course. And ZeroMQ.context, that is the first part every time you have to use ZeroMQ. It means I want to use ZeroMQ, I want to connect to the C++ framework that I know is installed on my machine, and I don't want to make mess with other applications that maybe are using the same framework. So, ZeroMQ.context just initialize everything. After that, you can create a socket. So, you can create here we can create here the socket, and here we have to specify the pattern. This is a reply socket. ZeroMQ.here. This is the pattern, okay? And then you have to specify a socket with the bind. Bind means this is the server, okay? Because we are listening on all the IP addresses on this machine, on TCP, on the 55554. You open a socket, we are listening. That's it. Now we have an infinite loop here, and we say, okay, my message is socket.receive. So I'm there and I'm waiting for a message. If the message is not there, I'm waiting on this function. Okay, so I'm blocked here until I have one message. Now it's funny to see the threading model of this application. How many threads do we have here? Well, one in the application. But then we have probably, we don't know, but probably one thread for each connection. And so what happens if we are not fast enough to consume our messages in this loop? Well, we have a queue under the hood, and all the messages are stored in the queue. Okay? So again, all this complexity is time to the developers. The message is a kind of string. I mean, in this case here, it's a string. On the network is a string with just a trailer in front of them. That's it. This is the message in ZeroMQ. And I can, because it's a reply, just send back to the client, after receiving the message, a response. So this is a server that is able to read something and reply with word. So if the reply is a word, you know that the client has to say hello. This is the client. It's more or less the same. The difference is the socket is not a reply, it's a request socket. Just a configuration, just to say to ZeroMQ, I'm using this pattern. This is the point. I'm using this pattern. That's it. Then I have again the connector. This time on localhost, just localhost. Can I use star here? Well, not really. This is the client, okay? This is not a server. This is not a binding. This is a connect. And we have a loop to send a few hello to the wire and receiving the response that should be word. This is the client that is the server. Let's see this in action very quickly. Yes. Okay, server is running, nothing is happening. Let's start the client. see that the client starts to send messages, and the server is starting receiving messages. Let's stop the client, and the server is reading again. Start again the client, and the server will start again. Do something fine now. Let's stop the server, and let's start the client. So the client is trying to send a request 1, but he's waiting because the server is not there. So let's start the server now. And now we start to send 1, 2, 3, and so on. So you see, we can start the client, and the client is waiting for the server. They are pressed, they are tuned, but we don't know where they are, and we don't want to know now.
The receipt is working.
Yeah.
Send asynchronous, but receipt is working.
No, well, attention, because the synchronous is something different here. Let me take back the example just for a while. Okay. Receipt is blocking, okay, because we are waiting to receive something, and some fine. Send is blocking. This one, but even the client is blocking. In the client, when we send hello, if the server is not there, we are waiting on the send. What is asynchronous? The asynchronous part is that when I have the socket on the server, so when I can send the message on the wire, in that case, this element is a different thread. So I'm proceeding with something else, and this messaging is composed. We probably have a byte stream somewhere in memory. ZeroMQ is taking this byte stream, is opening the real socket, is sending the packet on the network. This is something that runs somewhere, not here. So this is not blocking anymore. But if the socket is not there, yes, that's blocking. Okay, yeah.
So there's a way to specify an out of send.
Specify, sorry, there.
An out.
Well, yes, of course, you can specify timeouts, and you can specify also some kind of behavior in case of exceptions. Usually you don't want to do this kind of stuff. I mean, usually ZeroMQ is acting in a strange way. Sometimes it's trying to resend, sometimes it's trying to, that's raising an exception. It's trying, let's say, it's trying to resolve the problem in the best way it can. It can, easily, but you can control all the. Okay. Next, okay. Publisher subscriber. It's my favorite, actually. A publisher, again, is just this. Socket and publisher is the same. Okay, you want to use these patterns. And again, we have an infinite loop. We have a bind, so again, we have a server. We are writing the server here. And we generate some random number, okay? And again, send. Now, this time is different. It's not the same pattern because it's not blocking. I'm sending the message. If no one is listening, I don't care. I go ahead with the next one. So this sender is non-blocking even if you don't have a client. So this is the difference between this pattern and the previous one. The client, again, more or less the same. It's just a subscriber, okay? And we have a connector. This is the most important part in the client. You have to specify a filter. What a filter is? Filter is a string. So if the message starts with a string, you receive the message. If the message is not starting with a string, you discard the message. And it's just the start of the string. This is the filter. And you must specify a filter. So you have to specify a filter. If you want to read all the messages, you have to specify an empty string as a filter. But you have to say, with a sort of, I'm subscribing to these messages. And even if you are subscribing only one specific type of message, so let's say I want to receive all the messages that start with Python, well, actually ZeroMQ is sending you all the messages. And just the client is sending you to your code the messages that you are subscribing. And of course, you can subscribe multiple messages with multiple lines. Then again, you have the receive. We already know the receive. You have the send. and it's more or less the same. Very quickly, let's say this in action. The server is sending elements now, okay? I can show you. I have a print line here, so I can show you. You see? I'm sending, and there is no subscribers, okay? Now, let's go here. Now, someone is listening. Now we have to collect, for example, I think it's to collect 5 messages that start with a specific zip code. We are not lucky because speaking, we are not getting Sorry? No, it's just using the New York zip code if you don't specify anything else. I have to remove the print because it's slowing down actually the server, so we are more lucky. Well,
is that like receiving all that message?
Yes, all the messages. Yes, but we are waiting for the network. Could be. If you don't want to send a specific message, you have to use a different approach, not this one. The idea of the subscriber is that you receive everything, but your code is able only to read a specific, to be called on a specific message. It's not about the traffic on the network. It's only about when you want to call the code. The reason is this one. You could have, okay, we finally found. Good. You could have different applications that are subscriber of the same server, and you don't have to send the multiple messages to multiple applications on the same machine, for example. You can just receive the stream, and then ZeroMQ is calling this code for this message, this code for another message. So that's why the subscribers has to receive all the cloud. Then again, you have different patterns to reduce the traffic if this is your code. Okay.
In Redis, you subscribe the channel.
Yeah.
Server knows the client will subscribe that channel, and the server send message to the client specifically.
Yeah. Well, you can
reduce the network traffic.
Yes, of course, you can do that in ZeroMQ, but it's not part of the basic frameworks. It's something the basic patterns. It's something that introduces, let's say, not complexity, but something to increase not the pattern and the design of your application, but just the performance on the network. So that's the difference between these patterns that are logical and other patterns that are technical. Okay? Yeah?
Can the filter be a reference or a callback function?
Yes, but you have to implement that. Because you receive, the filter is only about the string. Then is, probably you don't really send a string on the network. You are sending something. It could be JSON, it could be an object, it could be whatever. So usually you can just read part of the message, and the message could be an object, and you can put something in the object. It depends on your application, but this is about you, it's not about you. So you're just using the string. Why the string? Low latency. It's very easy to segregate the string. It's very easy to filter just reading the first part of the string. That's why. A few things about subscriber and publisher. Always asynchronous, of course, because you don't have to wait even, so one reason more. You must specify always the subscription option, so you have to specify filter, empty string if you want everything. And you could have another problem, not just the problem on the network. The real problem here is that if you have a slow joiner, so you have a few slow clients, the server can be in danger. Why? Because you say it's asynchronous, so it shouldn't be a problem. Well, the problem is the queue. What happens if you fill the queue of the messages of the server? So the server is sending, he knows that someone is reading, but the server is not able to send back enough messages. So this could be a problem, an architectural problem. There are solutions, and hopefully we could solution. Last factor, pipeline. Pipeline can be simple, step by step, or can be more funny. So you can just have some parallel elements. So you have one execution point. At this stage, you have multiple workers, and then you want to collect back the data. The example that I have here is about the classical, number crunching problem. So you want to distribute some calculation with multiple machines, with multiple threads, multiple cores, and then you want to collect the result in one machine. This is the first part, so this is the object, the code that is able to send the message to different workers. Okay. If you see here, the funny thing is that you don't need to know the architecture of the worker. So you know that someone is going to do the work with the workload. So multiple elements are going to read the message that you're sending, but you don't know how many, and you don't know where they are. This communication is made by ZeroMQ. And again, we have just to specify the push as a pattern. So again, you specify the pattern and everything is automatically made. This is the worker, so the object that you see in the picture, 3 objects. So you can run a lot of these instances, and they are able to get messages from the previous code. In load balancing, that's very important. So if you have 10 worker, the ZeroMQ is sending you the first message to the first worker, the second message to the second worker. Okay, everything is balanced. And you have again the receive, nothing special again. And you can send back something if you want to send back something. Now, the last the last element, so the object is able to collect all the information. Well, this object is using the pool as a pattern, and this is able to wait, okay, all the messages from the workers. So this is again asynchronous, but here you are sure that if you send 10 messages, you are waiting 10 messages here. Using a particular fair queuing, we're going to see in a while. Just let me run this example. Ventilator. So the ventilator is ready to send something to the workers. We have to create some workers. One is created. Two, three. So we have 3 processes now as a worker that are waiting for a signal. And we can start here the name sync. So this is a collector, okay? Ready to go? So we are going to send messages, 100 messages to 3 workers, and we are collecting all the results. See, the worker started working, and here we go, the results. You see, of course, we have more or less the same output on different workers. If you want to run only one worker, no problem, okay? You can kill this one. This one. Again, the sync. Okay, and we can see probably a different execution time. Now is longer because we have 1 worker less. This was the execution time with 3 workers, execution time with 2 workers. So we are distributing dynamically our workload. They are in balancing, and they use a fair queuing system to distribute, to get the messages. How does it work? Well, if you have a push with 3 messages, 1, 2, 3 on this worker, another push here, and 2 other push on the last worker, well, you are reading from the workers, not just receiving the messages as they are, but you are receiving the messages in this order. So you read from one worker, then to the other one, then to the other one, then to the other one. So you're not just sending messages in load balancing, but you're reading messages back in load balancing. So the workers are waiting to send you the message in the right way. They must wait for you, for the sync. Must wait for you. Why this? Because you have to implement architectures that are sustainable. So you must have something that is able to scale and is able to stay up. These are the three basic patterns. You can mix the patterns, okay? You can decide to have a worker that is also a subscriber of something. So you can send back a message to the worker. You can do a reply from one-to-one. You can send back, after a pull, you can say, hey, worker, kill yourself. You can mix all these elements. You have, of course, these multiple sockets, send multiple elements, but this is what you can do, okay? Plug and play and plug and play. Now, in these examples, they're very simple, but there is a big problem. You're always doing while true, okay? So you're waiting always one message. And this is not real work, because when you start to play multiple elements, multiple sockets, and you want to have multiple architectures, you need to wait messages from different sockets. So you can't be blocked on a message. You want to be able to read two sockets, and you want to say, I want to react to the first message that is coming. And so you can use this object, the polder. The polder is something that you can see here, okay? Nothing special. But you receive the message, and you can just understand, using, okay, this, a dictionary in this case, which kind of message you receive. And so you can know how to act. But again, you are not blocked on a specific message. So again, you don't have to bring any lock to understand or to manage your application. It's made under the hood. I'll skip this demo because we don't have so much time and we have other 50 slides to see. So. This is the possible combinations, okay? We don't have only request response, request reply, sorry, subscriber, and publisher, or worker, puller, and pusher. We have something else. We have routers, we have DLR, we have a lot of different elements that we can use to play. They are not always available for each other. Okay? You can't send a publisher to a reply. It doesn't make sense. So when you implement a pattern, you have to be sure that a socket is made by two elements that are compatible. This is the compatibility list, okay? Nothing special about the law, okay? Then, a few words about scalability. You can scale easily, okay, so we use worker, so we see that we can put worker inside. And maybe we want also to redistribute this workload to other workers, so we want to make complex pipelines, okay? For example, we want to implement a proxy on a subscriber, so we want to get something from a network and send something else to another network. Pretty common again. How can we do that? Well, we can do that in code. So we can just open two sockets, read and send, okay? So we should know now how to write this code. Or we can use the devices. So there are few features that are available as objects, pre-made, but pre-included. So if you want, for example, a proxy, well, for the proxy we can use this object, this device in the ZeroMQ language. That is the queue. So we don't have, in this case, to write any while true in our application. And this is an application that is able to take a message from one socket and send the same message to another socket. I am subscriber for one message, and the same message I am the sender, so the publisher of the same message to another network. Dynamic scalability. We can use multiple sockets, so we can read a response from different servers. The problem is, I have to start the server, and I have to say to open enough sockets in my code. So it means I have to write 5 lines, connect, connect, connect. If I want to put another server, I have to open my code, and I have to write the 5th line. This is wrong, okay? It's not wrong, but it's strange when to increase the scalability, you have to open your code and do a cut and paste, because you have to close your application, you have to reboot your application. Okay, so another good pattern is this one. This is the classical broker model. So you have someone that is saying you have 5 subscribers, so you can ask for this service to these objects. If you want to put an object more, it's this one, this guy that is able to say to the request object, these are the services that you can use. So ZeroMQ is brokerless. We don't have a broker, but we can easily implement a broker if we need a broker. And this object can be a real broker. So it can do persistence, it can do whatever you want, logging, beefing, spoofing, I mean, depends what you want to do. So this is the last slide. This is my best definition of ZeroMQ. Okay, ZeroMQ is the socket as Python is to C++. So if you write an application in C++, you can rewrite it in Python in 5 minutes usually. And congratulations, because you wrote something in C++. I never be able to do that. And the same for ZeroMQ. If you want to write something with sockets, it's a mess, basically. If you use ZeroMQ for multi-threading, multi-processing, multi-nodes, it's extremely easy to write a good application with a good pattern. And that's it. I think it's time for questions.
What happens if one of the clients dies? We know what's happening behind the hood, because if the server or the pusher or whatever is sending data to a client, the client dies, this bit of information is lost, or somehow the server can acknowledge that and send the game to someone else?
Okay, well, there are different cases actually. The client dies before it receives the message. So you are trying to send a message, you are in the process to send a message, and the client doesn't respond. Well, the message is never sent. So the server is trying to try again. So the message is still in the server queue. You send a message, the client reads the message, and is moving the message from the buffer, okay, on the network to your application, your function, your technical function, whatever. Well, in that case, the server knows that the message is sent. Well, and then saying, if the message is not yet in your application, okay, and the client dies, the server is still trying to send you the message. But if the message it arrived just a tiny bit on your application, okay, it's not a problem of ZeroMQ anymore. So if you lose your message there, it's your problem. Okay. Why? Because we want zero latency. So we don't want 5 different callbacks. This is a good question actually, because ZeroMQ is very used in the financial market. In the financial market, a lot of people want persistence. So I want all the messages everywhere. So if something crashes, I have my queue persistent somewhere. This persistence is very expensive, so you have to choose latency or persistence. You can use a dealer if you want.
I can send acknowledge back, and server thinks someone is not processed.
Yeah, I mean,
until it receives an acknowledge.
Of course, I mean, you can use application persistence. For example, you can send a message, and then you can subscribe the client to say, okay, process your message, because I keep the message for you until you are implementing basically a transactional system. ZeroMQ is not transactional. You can't just say these messages are transactional. No, because you want zero latency. But it's very easy to implement a transaction.
Could I use ZeroMQ with some real-time Linux kernel patch, like ZeroMQ or something like that?
Yeah. I mean, real-time kernels usually are shipped with other MQ systems, especially MVQ or other implementation. I'm thinking about Red Hat Merit, for example, or the equivalent systems that support. But it's working pretty fine even with real-time kernel. It's not a kernel object, so you don't have any problem.
And on an embedded device with Arduino microcontroller, it's possible?
Yeah, nice. It's not a problem. It's I mean, ZeroMQ is a very simple code. If you want to see ZeroMQ core code, it's pretty easy. It's not too huge because it's just about managing communication. So it's pretty easy, and it's very portable. So it's not a problem on our end.
Thanks.
You're welcome. What else? Over there.
There was a PyPy talk yesterday, and they said that they already support a lot of C extensions, but often they don't know if something works or not because nobody has tried it yet. So does ZeroMQ work with PyPy?
Well, IT is not a perfect science, so you can't really understand what's happening. Python is using ZeroMQ as bindings, so of course you can have exceptions that are not mapped, or you can have strange behavior. But usually it's not a problem in ZeroMQ for the zero latency pattern. So because the framework by itself is not designed to be persistent every time, you have the same kind of exception independently of which kind of error you have. You can try to send a message without a cable, you can have a kernel crash, you can have a out of memory and the killer from the kernel is trying to fix things. But at the end in your application, you have always the same thing. It's not a big deal for ZeroMQ, not because it's special, but just because the design of ZeroMQ is very easy in that way. So usually you don't care. You have your message delivered or you don't have your message delivered. And you are waiting or you have an exception. Or you don't care. So it means you can't have something different because you don't have a transaction. Is it okay?
It was not the question. It was not the question. He asked about PyPy support.
Yeah, I mean,
PyPy.
let me be political sometimes. Come on. Let me be political again. But I mean, what's the side effect that you're seeing? Which scenario you don't want, or which scenario do you like to see? Because
we don't understand it. So maybe you can.
So I need to explain it.
Yeah.
PyPy is an alternative Python interpreter.
Yeah.
And it's written in Python, so far it didn't work with C extensions. But recently, they added support for C extensions.
Yeah. I mean,
It doesn't work with everything. So the question is, have you tried it?
No, I never tried.
Okay.
My response is it should work. Okay. The problem usually when you are trying to execute Python in Python is that you can have a different exception from the Python running as an interpreter or Python in Python itself.
I see. Okay.
But in ZeroMQ, the response was you can have a different exception, but you shouldn't care because at the end your application can run in only one way. That's the point. So maybe you have a different exception, but you don't care, or you shouldn't care.
Has there been any work to implement the FBI protocol on top of ZeroMQ?
I don't think so. I never saw any MPI implementation with ZeroMQ. And I think they have competitors, to be honest. They are, same idea, multi-language distributed and multiple OS support.
Can you actually secure the socket somebody?
Like with encryptions or? Yes, but there is an object called envelope that you can use to do these kind of things. Usually you shouldn't. That's the point. ZeroMQ is not designed to be exposed on the network. So don't think to use ZeroMQ to implement your web server or to implement public services. The idea is to use ZeroMQ inside your applications and maybe inside your protocols in some cases on the C6 channel, these kind of things. The idea of encryption is possible. It's not impossible, but is not really about zero latency. That's the main problem. Yeah.
Yeah, I have actually two questions. The first one is how it could integrate with Postgres. And the second one is if there's a way of querying the status of each node of the queue runtime, for instance, asking, I mean, what the activity is, in order to monitor the stages of the queue, of the whole queue?
Yes, you can, but you are trying to implement a brokerful application. So the point is you are using Postgres probably to persist the messages, and so you want to know how many messages are there and there and there. You can do that using the dealers, but again, if you're doing that for all the infrastructures, you're using the wrong tool probably, because you're using a brokerless tool to implement a brokerful applications. You can use, Intro or Enterprise ESP that are doing that by the tool. But you don't have the benefit of the zero broker and low latency subsystem. Okay.
So we are running late. It's time to thank Francesco.
Yeah.